A compared to triplets. So we're given 6 numbers. We're comparing these pairs of numbers, and we have to count the number of the pairs such that the top element is greater than the lower element. So you just have to implement this one line in Python, whatever. Pretty straightforward. Yeah, that wasn't immediately easy problem. Okay. Problem B, forming a magic set. So we were given a 3 by 3 square with some numbers on it, and you had to transform this square into a magic square. Magic square is a common magic square where the sum of each row, diagonal, and column is the same. Well, I guess the easiest way to do this is just to generate all possible magic squares, and then given the input square, you compare it to every magic square that you found and calculate what is the distance, and take the minimum of all this distance is. And generating all magic squares is not hard because there are only 9 factorial possibilities for placing 9 different digits in this square. And you can also do it by hand. There are actually only 8 magic squares, if I'm not mistaken. So find the magic squares, and in some way then find which magic square is closest to the square that are given to you, and calculate the difference. Alright, problem G, minimum loss. So in this problem, you are given an array of elements. And you have to find 2 indices I and j, such that, well, I is less than j, bi is greater than bj, and bi minus bj is minimized. Okay, and there are many ways to solve this problem. You use some fancy data structure to find this guy, but I guess one of the simplest solutions would be just to iterate through these elements from left to right. So look at this element right now. Okay. And now I need to find among these elements to the left, what is the smallest value that is greater than the value of j? So if I store these previous elements in a set, you can easily find this value by doing binary search in the set. The set structure in C++ has a function called upper bound. Which returns the first element that is greater than x. So you use this function to find the best candidate for I for this particular j. And you do this for all set j, and take the minimum of them all, and you find the optimal answer. But you could also do some range minimum query with this guy or something like that, but that was not necessary. Cool. Okay, let's do problem J. Counting special subjects. So in this problem, you have a cube of numbers. each cell of this cube was an integer, and we call a subcube special if the subcube has size k, and the maximum element of this subcube is also k. And we want to count the number of such subcubes, special subcubes. Once again, there are many different ways to approach this problem. One way is to use dynamic programming to calculate for each subcube what is the maximum element of this subcube. So you could do something like f x, y, z, k, which means what is the maximum element of a cube of size k that is whose topmost left further corner is x, y, and z. And you can calculate this value in terms of smaller f's. In particular, if you're looking for the maximum element of a cube of size k, you can just take the maximum value of all subcubes of size k minus 1 that is contained inside it. And there are only 8 such subcubes. We can just take the maximum of the maximum element of all these 8 subcubes, and that will give you the maximum element of the whole cube. Okay? So each f can be calculated in constant time. We have n to 4 states. So this will be our overall complexity, and this was enough to pass the time limits. Okay. Okay, let's discuss probably the most boring problem of this problem set. Probably immediate present. Okay. Did anyone find a really nice, elegant solution to this problem that doesn't involve a lot of casework? My solution involves some casework. The author's solution also is not much better. This problem at first looks pretty easy. It is actually very tricky. You have to be very careful not to count the same subset more than once, and also you have to be careful not to count invalid subsets. So basically, in this problem, you were given the lengths of different sticks. Sticks could have the same, different sticks could have the same meaning. What you want to do is count the number of ways you can choose 6 of the sticks to form a square. First thing to notice here is that there are only 2 possible configurations. There are only two possible ways to form a square with 6 sticks. You either pick, you either choose 2 sides and assign 1 stick to them, and then you fill the other 2 sides with 2 sticks each. Or you use, for 3 sides of squares are formed by a single stick, and the last side is formed by 3 different sticks. Okay. So basically you have to count the number of possibilities for these 2 cases. And, well, I'm going to show how to count the number for this case, and I'm going to leave this case for homework. It's just a boring case where we're having to be careful not to double count and remove some sets that we should not be counting. Yeah, I couldn't find a better solution to this. So if you find a solution that doesn't involve that many case analysis, feel free to share the solution. Okay, so how do we count this kind of configurations? Well, suppose we're looking at the number of ways to form the square of length f. Okay. let's pre-process. Let's pre-calculate two different arrays. Let's call Qx the number of sticks with length x. And I'll call Q2x the number of different pairs ij such that the sum of I and j is equal to x. Okay, I remember. So basically, there's the number of ways to form x with a single stick, and here's the number of ways to form x using two sticks. Okay. All right. So the difficulty here is counting the number of ways to form L using 3 sticks. Right. So one thing we could do is, okay, let's choose the first stick we're going to use. And my stick has length z in it. So you might be tempted to say that the number of such configurations that has length L and uses the I stick whose length is z is Q2 of L minus z. Right? This is intuitive, but this is far from being the correct answer. There are some problems. First, we are considering here the cases where z is also used in this pairing. So, for instance, if L is 5 and I'm looking at z equals 2 to 1 is one possible answer, but these two could be the same as these two. So you have to be careful. Right now we're counting this data. We shouldn't be. So how do we remove this invalid choices? Well, basically what we're counting wrong here is the case where I use the same stick twice. So if I use the same stick twice, how many configurations are there that form L? So using z. So this last guy has to be L minus 2z. Right? So, okay, you might try fixing this by subtracting Q of L minus 2z. Right? Okay, this is almost correct. You have to be careful of the case where 3z equals L. Because in this case, you will be subtracting also the case, you'll be subtracting twice the case where this guy is also equal to z. So if z is a third of L, you should subtract one less from this guy. Okay. Alright. So right now, this value does not include any invalid choices, but there might be repeated ones. Yes, how do we take care? Actually, no. If I fix the index of the first stick that I choose, and this actually counts correctly the number of configurations. The number of ways I can choose the remaining two guys to form L. But if I sum this value for all sticks, then I'll be double counting, because I'll be counting the triple I, J, K, and J, I, K, and K, I, J. I'll be counting this guy as separate solutions, but they're actually the same, because order doesn't matter. But actually, every such triple will be counted 3 times. So what we can do is just sum this value for all values for all different sticks, and then we divide by 3, and this will give me the correct number of ways to form one side of length 3 of length L using 3 sticks. And then you do some combinatorial things to choose which case to use for these three sites. It's basically Q, L, choose. So as you can see, there any tricky case had to be you have to take care of. And this case is not very different. You have to do similar stuff. Okay. Any comments on this problem? Yeah, I really hate this problem. Anyway. Okay, let's do problem I. I'll see us with this. Okay, so the key to this problem was figuring out how to use the information that the arrays will be generated randomly. I heard that there are some deterministic solutions that work for every array, but if we consider that each array is generated randomly, there are easier solutions. So the intended solution is as follows. Suppose we have three arrays B and C, which are the input arrays, and we are interested in the triples I, J, K, such that I equals DJ equals CK. Okay. Well, it turns out that the number of such triples is not that large, right? So suppose that each array is generated randomly, and IA is equal to I with probability 1 over n. So, given a triplet ijk, what is the probability that these three elements are equal to each other? Well, this guy has to be equal to this one, right? And this happens with probability 1 over n. And this guy also has to be equal to this one, and that also happens with probability 1 over n. And since these two guys are independent, the probability of a triple to correspond to elements that are equal is 1 over n squared. Right? But how many different triples are there? There are in Q, right? So what is the expected number of such triples in total? This is the product. That. So actually the expected number of triples that correspond to elements are all the same is m. If the arrays are generated randomly. Okay. So we view this fact, and the first thing we do is probably generate all such triples. And in order to do this and not take NQ time, what we can do is for each array and for each value, you count the number of times this value appears in each array. And also to store the indices of each appearance. And with this, you can just, for each value, you see, it's just a matter of combining, right? If I want to count the number of triples that are equal to 7, then you look at the appearances of 7 in this array. So it's 7 appears in positions 1, 3, 5, and B appears in 4, and C appears in 2 and 8. So every combination of every possible choice of this, the first of an element of A, element of B, and element of C, will form a valid triple. So, and finding this array, you can do it in correct time. So you can generate all such triples in O of n squared plus the number of triples, which is n. All right. once we have all triples, how do we find the longest common subsequence? Well, from here there are some different approaches. One of them is to look at each triple as a vertex of a graph, and you create an edge from one triple to the other if this triple can go after this one in the sequence. In other words, this is I1, K1, K1, and this I2, K2, K2. You create an edge from this guy to this guy if I1 is less than I2, K1 is less than K2, and K1 is less than K2. There are no n squared edges in this graph, so you can just find the maximum path in this graph. And since this graph is cyclic, this can be done in any account, in the number of edges. Or you can also do some dynamic programming by first sorting each triple lexicography. That also works. Okay. So the expected complexity of the solution is as great. Okay. So yeah, as I said, there are more complicated solutions that doesn't rely on the randomness of each array, but since the problem setter gave us the information, that we can use a more simpler approach. Okay. Any questions, comments?
What will happen if it was not randomly generated? Right?
Yeah.
What is the problem?
What
is the problem with this?
What is the problem with this solution?
Will get more complicated, the solution.
The problem with this solution, but you understand that this solution wouldn't work anymore. I mean, it still works, but it will get slow because the number of triples might be large. In particular, if every element is the same, it will have n cubed such triples. So the complexity will be n to the third power, at least. Okay. You can solve this problem without randomness, but I haven't looked into it yet. If you want to know more about it, talk to Berg. They solve this problem without using the randomness information.
We use it.
You use randomness.
But I think it would for greater, much greater value. It's just that you use n squared after n square of the size of the random vector, right? We use n log of the size of the random vector. Still relies on randomness,
Okay.
not as much.
Yeah, I thought the Wiz solution would work for any input. Okay. Yeah, the general problem that should be complete. If you have k sequences of length L and when you find the longest common subsequence, this is an NP-hard problem. So yeah, I won't do it. It doesn't surprise me that there are no efficiency issues. Okay, any other comments, questions? Hey, problem E, 3 points. Okay, so in this problem, you have a tree graph that is rooted. And each vertex contains a certain amount of points. 2, 1, 3, so on. And this is a game between 2 players. And the only allowed operation is to pick a node. This one. number of points from this node and add them to the parent of this node. So unbounded pool will be to move 2 points from this guy to the parent. Okay. So the problem not only asks which player had the winning strategy, but also it asks you to answer this question by making some small modification of your arc. And the modification was you could pick a vertex, remove the edge, connecting this vertex to this parent, connect this guy somewhere else, like here. And you need to answer the same question. In this configuration, who has the winning strategy? Okay. And the player loses if he has no valid moves. Okay. Cool. So, yeah, in order to solve the problem, you have to first think about who has a winning strategy for a fixed trade. Okay. Who here is not familiar with some basic meme theory? The meme game. You have some piles of stones. It's a similar game actually. It's a two-player game, and on each turn you can pick one pile and remove a positive number of stones. And if a player has no valid moves, he loses. Okay. So it is a well-known fact that a configuration of the main game is winning if and only if the binary exclusive OR of the values of the number of stones in each pile is greater than 0. This is 3, 0, 1, 2, 3. This configuration is winning for the first player if and only if it's 0, 1. Is this me? I'm going to write this to represent the binary source. 2, 3, 0. Well, if you're not familiar with this, then I could spend I will need some extra time to explain why this holds. But if you don't know about this, it's a really cool theory. You should look into it. But yeah, I'm going to use this fact in order to solve the problem. All right. So for this game, it turns out that we can only look at vertices that are at even distances from the root. This is 1, 2, 2, 2, 3, 3. So let's call this vertices. Let's call this kind of vertices odd vertices, and these vertices even vertices. So I claim that if you look only at vertices, at odd vertices, and you consider the amount of points of each vertex as a pile of min game, then the position is winning for the first player if and only if the min game is also winning for the first player. Okay. The really if part is easy. So suppose that if I look at the piles of even of odd vertices, the position is winning for the first player. Actually, the converse is easy. If you construct this secondary game where the pile of each, the number of stones in each pile is equal to the amount of points in the odd vertices, then if this configuration is winning, then you can show that this configuration is also winning. And what the first player needs to do is basically play the nin game. So the first move that the first player does is make a winning move in this nin game, which will correspond to selecting the corresponding node and making not this one. Take the corresponding node and make the exact same move you would do in the nin game. Now the second player has two choices. He either makes a move on an odd vertex or an even vertex. If he plays on an odd vertex, then he will be playing our name game, and we know that we win this game. If he plays on an even node, then what I can do is basically cancel this move by making the exact same move on the parent node. So if he makes a move here, let's suppose that this node has 4 points. This is an even node. If the second player makes a move here, let's say he moves 3 points in parent, then I am always able to repeat the same move to the parent. Here, and that holds because this vertex is even. So this vertex always has a parent that is not the root. So this reflection is always possible. So whatever move the second player makes on even nodes, they can always make a similar move on the parent node, and the state of odd vertex is not changing. Okay. And the second player cannot keep doing this indefinitely because eventually you will run out of points on even verses. So he will eventually need to start playing your main game. And you know that this game is waiting for you. So this is clear. So this is the strategy for the first player. If this name game is winning for him. Now, if the name game is losing for the first player, then we can show that this position is also losing for the first player. And basically, because the second player can do the same thing that the first player would do if this position was winning. If the first player makes a move on an even node, then the second player reflects this move, and this changes nothing. If I make a move on an odd vertex, then I will be playing a losing move in this game, and the second player will make the corresponding winning move in the resulting configuration of this game. So, given the configuration of vertices, this configuration is winning if and only if the binary XOR of the odd vertex is different from 0. Okay. Cool. So now we know how to check whether a given configuration is winning or not for the first player. Now, in order to answer the queries of the problem, what we need to do is basically have to quickly recalculate the binary or of the odd vertices when this modification happens in the graph. So this is not really hard to do, right? Because if this vertex in the original graph was odd, and in the new graph is also odd, then the binary OR of the odd vertices will not change, right? Odd vertices will remain odd, even vertices will remain even. So the value of the binary OR doesn't change. The binary is close to 4. And if this is an even node and it becomes an odd node when it makes this transformation, then all you have to do is, instead of considering the binary exclusive OR of odd vertices, you consider the binary exclusive OR of even vertices. So if you just calculate or pre-calculate for each subtree what is the binary XOR of even vertices and odd vertices, you will be able to answer each for constant time. Right, just a matter of some calculations of removing the even vertices and adding the odd vertices or the other way around. Is that clear? Questions? Okay. problem C, black and white tree. Oh yeah, one thing I forgot to mention is that you also have to check whether whether this transformation forms a tree or not, because he might also want to connect this guy to a guy on its own subtree, and this clearly doesn't form a tree, so you should print invalid in this case. And in order to verify, in order to check whether this happens, you only have to check whether the new parent belongs to the subtree of this guy. And you should recalculate the pre-order indices and the post-order indices of all vertices. You can check if one guy belongs to the subtree constant time. Okay. The pre-order index of this guy has to lie in between the pre-order and post-order of this guy. Okay, pharmacy. Problem C basically involved two different problems in a simple problem, so it was quite plenty. Okay. So you were given a graph, and you know that this graph is bipartite, but some edges of this graph will be erased. So what we'll actually have is some connected components which are all bipartite, because if the original graph is bipartite, then each component is also bipartite. And what we want to do is to color each vertex either white or black, such that the difference between white node and black node is minimized. And you also have to connect this component somehow in the end. That's not really difficult. So the main difficulty of this problem was basically to find one possible coloring of the verses so that the difference between the number of white nodes and black nodes is as minimal as possible. That's all valid. Okay. So the first thing to do, for each component, since we know this is bipartite, there are only two possible colorings. If you color this vertex white, then the color of every other vertex is already defined, because vertices connected by an edge has to have different colors. Right? So, and since this vertex can be either white or black, for each component we have only two possible colorings. Okay, so first thing, you just run a search on every component and calculate the number of white and black nodes in each configuration. It will be the same like that actually. If one coloring results in 3 white nodes and 5 black nodes, and if you flip the colors, we will have 5 here. Right? Okay. Let's assume without the possible generality that we pick a coloring for each graph such that the number of white colors, number of nodes with white color is minimum. Okay. So we have W 0, black 0, 1, black 1, and black n. And let's assume that W0 is less than or equal to V0 for each I. Okay. So, what can we do here to find the minimum possible value of the absolute value, the difference between black nodes and white nodes? Well, we can just, since I know that W0 is less than U0, I know that if I flip the colors of this component, I would increase the number of white nodes. Right? and I want to know which values of the sum of white nodes are achievable. But this is basically an abstract problem. Right? I want to decide which. I can choose whether or not to flip the colors of a component. And when I do, I increase the number of white nodes by a certain value. And I want to know from all achievable values, which one is closest to either two. Right? So you could look at this as an abstract problem. But the issue here is that we have n different components, and you want to, the array you're trying to construct also has like n. So the standard dynamic progressive approach will take n squared times just too slow. The key observation here is to realize that if you look at the differences between v0 and w0, which is basically how much we gain by flipping this component, turns out that the number of such differences, the number of different differences cannot be too high. When there cannot be more than 2 square root of n different differences among these guys, for example. Because we know that if I sum all these differences, the sum cannot exceed n, right? Because each difference is the difference between the number of black nodes and white nodes in the graph. And this difference is positive because I'm supposing that w0 is less than v0 for every I. So this means that for each component, the difference between the number of black nodes and white nodes is less than the number of nodes in this component, right? Has to be. So if I sum all these differences, the sum of these values cannot exceed n. And what happens if I assume that there are over 2 square root of n different values? Well, the minimum sum we can get using 2 square root of n different values is this, right? 0 plus 1 plus 2 square root of n. If I have over 2 square root of n different values, this is the total sum has to be at least this, right? Each time a new difference appears, it has to show up the sum. But this is equal to 2 root of n plus 1 to 2 is equal to 2n plus 2 root n, which is perfectly greater than n, which cannot happen, right? Because I know that the sum of all these differences doesn't exceed n. So what we found out is that there can be many different differences among these n differences. Okay. So actually, in our abstract, we have all of root of n different values we can add. Yeah. So the difficulty here now is that we might have more than one of each component. So how do we deal with that? Okay, I'm only interested in I want to know whether each sum of them is achievable or not. Right? So suppose that at some moment I know that using only the components from 0 to I minus 1, I know which sums are achievable. Okay, I have an array achievable, which tells me that with the first I components, I can get a sum of value S. Okay. Now what I want to do is, how can I update this achievable array to also take into account this pair, wi, yeah. Okay. So what we're going to do is calculate for each such S, what is the minimum number of this value that I need to achieve S. Let's not talk about the reasons these. Let's just suppose that we have a standard backpack problem. We have at most for n items, and each item has their value quantity, and I want to know which values are achievable using only this kind of elements and restricted to this quantity each element. So suppose that until I minus 1, I know which values are achievable. So if I'm now looking at element I, what I will do is basically do a mini dynamic programming inside this dynamic programming. So I will calculate a value of minimum of S, which means what is the minimum number of elements of this type I need to achieve S. Knowing that I already know how to achieve values of S using the elements from I-1 to 4. Okay. Suppose my achievable array currently looks like this. 1 is always achievable, 0 is not achievable, 1 is achievable, 2 is achievable, 3 is achievable, and something like that. Doesn't look like that. Okay. So I know how to get this using only elements from 0 to I-1. And then once you update this array to also take into account the ith value. Okay, so using vi, what is the minimum number of vi that I need to achieve 0? It's 0 because this value is already achievable, right? Let's, for example, take vi equals 3. Phrase it back down. And I can achieve 1 using only 3's, right? So this guy remains unachievable. I also can achieve 2, but 2 is already achievable, so the actual number of elements is 0. Okay. Now, in order to reach 3, I can use a solution that adds to 0 and add 1 element vi to get 3. Right? So 3 is achievable using 1 such element. Okay. Now 4 is unachievable, and I cannot use solution for 1 that I found because for 1 is also unachievable, so we gotta use this infinite as well. Now, for 5, I know that 2 is achievable, right? So I can achieve 5 using 1 guy. Let's suppose 6 is not achievable. And 6 is currently not achievable, but I can achieve 6 using the solution for 3 I found now. I know that 3 is achievable using 1 vi, so 6 is achievable using 2 times vi. So I can get 6 is 2 guys, and 7 is achievable. Do you guys understand how I built this array? Next plane, very well. But the thing is that this array will tell me the minimum number of vi's I need to achieve new values. And now, whether or not these values are actually achievable, I just have to compare whether each of these values is less or equal to each value I have. That makes sense? Because if I can get to 6 using 2 times 3, but I only have 1 3, and this value is not achievable. Right? So once we have this array, we can update the achievable array by checking whether the current value is achievable, but I can achieve it using less than qi times vi. Does that make sense? So this guy becomes achievable, this guy becomes achievable. If qi is 1, then this guy doesn't become achievable. Cool. So each step can be done in linear time, and since we have at most 2 square root of random different elements, this achievable array can be found for every element and times square root of random time. Okay. And it's not hard to modify this to also remember for each sum what is the guide that you need to take to achieve the sum. You just have to memorize. Similarly, in the knapsack dynamic program where you also have to print the valid solution, you can do the similar thing here. For each position, you remember what is the last guide that you used to achieve the value. By doing this, you can reconstruct the answer, which is you can figure out which components you have to flip in order to achieve the sum of white node that is closest to number 2. Does that make sense? Okay, that was the hardest part of the problem. So by doing this, you figure out what is the minimum absolute difference between black and white nodes. And you can also find the coloring for each component that results, that gives you this minimum absolute difference. The only thing you have to do now is to connect these components. And in order that you make sure that they still stay by connected. And once you know the color of the vertex, the only thing you have to do is connect black nodes with white nodes, and number 2 nodes with the same color. And well, you have to be careful here because given 2 components, they not necessarily always have. Then it may not be possible to connect these 2 components because all the vertices of these components might have the same color. But we know that it's never optimal to have all components of the same color, because we could just make one component fit the color and have a better answer. So we know that if we look at all components, we have at least one white vertex and one black vertex. And we can use these 2 as pivots to connect all the other components and make the whole thing connected. Okay. So yeah, very lengthy code, because the problem basically asks you to print the result, print the optimal solution. Yeah. That's pretty much it. Any questions? Okay. That's the problem H math program. So in this problem, we have 3 and you were giving a bunch of queries. Each query gave you a subset of this versus the problem asks what is the minimum number of paths you need to build such that the set of edges that this path creates makes this subset connected. So one way would be to do something like this. This is a pretty stupid example. Okay, so in this case, we could do this using two paths. You could use this path and just this path. And that will make the whole subset active. Okay. How to solve this problem? Well, the first thing to notice is that the set of edges that need to be restored, I know how Steve calls it. But the set of edges that you need to consider, well, it has to be connected. It has to form a connected component. It doesn't make sense to have one edge here, another edge here, and this guy will not be connected because this will mean that there's some vertex here and some vertex here that are not connected with each other. So the set of edges that we need to restore forms a connected component, and since the ratio is 3, this connected component also has to be a tree. Right? And moreover, we know that the leaves of this subtree must belong to the subset that's given to you. Right? Because if that's not the case, then clearly these edges not necessary. Right? There's no need for me to restore this path if it connects to a vertex that doesn't need to be connected. So I can only consider this subtree that is connected, and that I know that about the subtree, all leaves must be vertices of the subset that the query gives you. Okay. So given this tree, what is the minimum amount of paths that you need so that you restore every edge of this path? Well, one lower bound on the number of paths is the ceiling of L over 2, where L is the number of leaves in the subtree. Why is that? Because each path can only cover at most 2 leaf edges. Right? That's called leaf edge, the edge that connects to it. And since each path can at most start at a leaf and end at a leaf, and we want to cover every single vertex in the subset, then this must be an upper bound. Right? Each path can cover at most 2 leaves. And it turns out that this is actually always the optimal solution. So why is that the case? Consider any set of L over 2 paths that connect that uses every leaf edge. It doesn't necessarily have to pass every edge of the tree. The only thing that matters is that each path covers these leaf edges. Okay? And that's always possible. Just pair each leaves and make a path between these pairs. Okay? Yeah. If that covers every edge, then we're good. But it might be the case that there are some edges that are not covered. Right? For example, if my subtree looks like this, are the vertices you're interested in, you could end up choosing these paths. Right. They cover every leaf edge, but this edge remains uncovered. So what we can do is modify this path a little bit so that it also covers this edge. Okay. So consider any uncovered edge of this subtree. Clearly, these two guys cannot be leaves, right? Because by construction, my paths cover all leaf edges. So these guys are not leaves, which means there is a subtree to the left of this edge, and there's another subtree to the right of this edge. Right? And well, if this is a subtree, this means that there is at least some node to the left of this edge that is a leaf. Right? And this leaf is covered, which means that there must be another leaf here that is paired to this guy. Right? Because we know that this edge is not covered, and there must be a leaf here, and this leaf edge must be covered. So there is a path that starts here and stops somewhere. In worst case, it stops at another leaf edge, and another leaf, so there must be something like this in this graphic. Oh, it could be the case that there's only one leaf here. But that only happens if this forms a path. And it's pretty trivial to fix this. You just make the path go through the edge. In the other case, this must happen. Same goes for the other side. There must be two leaves here that are connected by a path. It doesn't go through that edge. And now, what we can do to cover this edge, let's call this AB. Well, instead of connecting A to B and C to D, we can connect A to D and C to B, for instance. Do you have another color? Instead of connecting A to B and C to D, we can do something like this. Right? And I claim that this solution is at least as good as the pink solution. Right? So the only thing that I need to prove is that every edge that is covered by the pink path is also covered by the yellow paths. And this doesn't hold, right? Because since there's a path from A to B, and this is a tree, then this path has to go through the common ancestor of A and B. Right? The lowest common ancestor of A and B, somewhere around here. Now, considering this subtree rooted at this guy, okay? Then this thing. And same thing here. There must be a vertex that is the lowest common ancestor of C and D, and this path has to pass to this guy. Right? But this guy is a common ancestor of A, right? In particular, this is A ancestor of A. So the path from A to the root must pass through this guy. Right? So the yellow path actually looks like this. It goes here. And then moves upwards or rightwards. Same thing here. The yellow path actually does this and go backward. Same thing here. And here. So the yellow path actually covers every edge that is covered by the pink paths. This solution must be at least as good as the previous one. And I covered one extra edge. So if there are any other remaining edges to be covered, I can apply the same procedure and cover every single edge in this subtree. Is that clear? So this is overbound, and I just proved that it is always possible to achieve one, to find a set of algebra 2 paths that cover every edge. So this must be the optimal value. Right? This is the minimum number of paths to connect all of these guys. So this is the answer to the query. You just have to find the value of L, which is the second half of the problem. Okay, so given a subset of vertices, how do I check whether a vertex is a tree, is a leaf or not? Well, there are actually two cases. The first case is when, if you look at this vertex and it's subtree in the original graph, there must be no hidden vertices in this subgraph, except for this one, right? If there is any hidden vertex here, then this means that this edge, this path exists, and this guy is not a leaf. So, if there are no hidden vertices in the subtree of this guy must be a leaf. But that's not the only case. It has to also be taken into account this case. So that this vertex is not there. In this subtree, this guy is also a leaf, right? So how do we detect this guy? Well, if this guy is a leaf, this means that there is a single edge here that connects him to the rest of the subtree, right? So this guy is a leaf when all other vertices of the subset lies in the subtree of a child of this guy. So if something like this happens, then this means that this guy is also a leaf. And you have to take this case into account as well. Okay. And you can check. Let's see. For this case, the way to verify that this guy is a leaf is first realizing that there's only one possible. If a leaf like this exists among the vertices, the subset that is given to you, then there is only one such candidate. It must be the vertex that is closest to the root. Right? That is the only possible candidate for a leaf in this configuration. So you take this candidate and you have to check whether this guy has a child that contains every other vertex in its subtree. And you can do that again using that trick with pre-order and post-order indices. You calculate the pre and post-order for every vertex in this graph. You remember for each other hidden vertex what is the lowest pre-order index and highest pre-order index. And basically what you have to check is whether higher post-order index. And what you have to check is whether this guy has a child whose pre and post order contains the pre and post of every other vertex. So you can do, so if the subset has when asked, then you can do that in all of that time. Right. Okay, the other case is a bit trickier. So in order to check whether a vertex contains another vertex in the subtree, what you can do is, once again, use the pre and post order trick. You build some data structure that allows you to whenever you're given a vertex, you add one to the position that corresponds to the preorder of this guy. And now, if we want to check whether this guy contains any vertex, just look at the sum of the values between the preorder of this guy and the post-order of this guy. There is some vertex in this subtree that this sum will be greater than 1. Okay. If I add 1 to the pre-order positions of every vertex in this graph, and then go to this value and sum the values between the pre-order and post-order indices, then this sum will be greater than 1, right? Because I'll be counting these guys once for each guy. So you could check this in log time using your favorite data structure, favorite tree or 7 tree or whatever tree. And the other case you could like this. So we can basically process any given subset and at most n log as log n time. Yeah, and in this time you can count the number of leaves in this subset, and then you only need to print the ceiling of this value by 2. That's pretty much it. Yes.
If you did a recursive DFS, you would get runtime error because the stack would overflow. Yes.
In the original tree?
Yes.
I'm pretty sure they did recursive DFS, so you would not get runtime error.
Just change to iterative and move fast.
I can double check, but I didn't have these problems. Yeah, sometimes when the graph is too large and the problem setter is nasty and creates a cascade like this, a path of length path, and you run a DFS starting from root, you might get screwed because you would create the stack size here will have a length path, and this might explode your stack memory. So sometimes this happens, and you have to work around this somehow. You either implement your DFS aggressively, or you do some other search. But I didn't have these problems in this context in particular, so I don't know. Anyway, any other comments?
So,
Go ahead.
would it be possible to reconstruct the answer? Because this proof is really not so direct to reconstruct the answer.
Good question. I'm not sure about the great question. Actually, I think there is a way. If I'm not mistaken, I think I've met a problem like this before where I had to reconstruct the path. Or was it just a count? I don't know. Hazel, do you know where is Hazel? Damn it. Yeah, good question. I don't know how to answer that. Any other questions?
Caiu o Renzo, caiu a maratona, velho. Aí, o homem.
Okay, let's have a quick break and then I'll explain the last problem.
É que chegou o Google, cara.
Bem completo.
Só, cara. Mas eu vi. Cara, só acho que folhas. Não, porque esse número de folhas dessa especial. Esse que é o problema. Desde que porque a resposta é sempre. Então, você tem que ver que achar essa água.
Okay, so let's solve the last problem, problem F. Can leave that solve this. Okay. So this problem, we had an array of numbers, and at each time you could pick a number, change it to 0, and by doing this, you add to your score the sum of all elements that comes before it. Okay. There are some restrictions limiting which elements can choose at any time, but I'll talk about those later. This is that they didn't change much of the problem. And basically, what we're trying to do here is maximize our score. Okay. So in problems where So in problems like this, where you have to find an optimal ordering, there are normally two usual approaches. The first one is trying to find one ordering that always works. This would be a greedy solution, but it doesn't seem to be the case for this problem. If someone knows a greedy solution for this problem, please talk to me. And the other usual approach is to apply dynamic programming. And if you want to apply dynamic programming, then we need to store in our state enough information about the decisions we made so far so that we are able to compute the impact of our current choice in the final result. So let's see how we can solve this problem using DP. Well, one natural thing to use as a state of mind of our DP is some interval that I want to work on. Suppose I have this interval, this array from L to R, and I want to maximize the contribution of this interval to the final result. Okay. Now, the thing is that only this information is not enough, because elements that are to the right of this interval can change how the value that we add to the result here. Right? Whenever I choose an element to the right of this interval, then we will add to the result the sum of the elements that were not chosen here to the interval. On the other hand, elements that are to the left of this interval are not very interesting because they have no impact on the contribution of this interval, right? But the cool thing is that, okay, this guy changes the solution for this interval, but it doesn't really matter who this guy is. The only thing that matters is basically how many of these guys are there. Okay? So I'm going to add information to this state of mind. So my dynamic program will have the following state. The interval whose score I want to maximize, and how many guys are there to the left, to the right of this interval that are still not chosen. Okay? So how do we find the value of this guy? Okay, so you have this interval, and basically what we're trying to do is find an order in which to choose the elements to produce the maximum result. So at this moment, I have basically two choices. Either I pick one element from this interval to go first, or one of the k elements to the right to go first. Right? And let's just say that I haven't chosen any element in this interval yet. If I decide to choose some guy to the right of this interval before choosing any element in this interval, then the answer that we get is basically f of L r k minus 1 because I take one element to the right, plus the contribution of this interval, which would be the sum of these guys. Right? Well, I'll call it S from L to R. Okay? This is one possibility. Another possibility is that I decide to choose some guy from this interval first. Let's say element I. Okay, let's not care about whether I can pick I or not. I'll talk about that later. So what do I get if I pick I first? Well, if I pick I, then I get the sum of all these guys that come before I, but after L. The sum of these guys will be added to the final result. Right? So I will have f of the sum of L to I plus 1, right? And then I'll basically have the same, I will apply each of these intervals I can solve recursively using the same idea. So for this interval, which is L to I minus 1, how many guys to the right they have that were not chosen yet? It's k, there are k elements to the right of R, that are not chosen yet, plus this guys, right? They were not chosen yet. That would be k plus R minus I. But this will be the maximum contribution for this interval. Okay. And same thing for this interval. The contribution of this interval to the final result will be f of I plus 1R. And the number of elements to the right will be k2. Okay? Fine. Does that make sense? Okay, so the value of L is basically, these are all possibilities I have. Right? Either you pick an element right of this interval or here. If I pick an element to the left, the matter doesn't change the contribution of this interval to the final result. So this is basically the only choice I have. So the value for this whole interval is basically the minimum of these two guys. Maximum, yeah, we try to maximize. Yeah, the basic case is fairly easy, right? Our element is contains a single, or interval contains a single element. Then we have two cases. Either the I is positive, which is good. In this case, it's much better to take all these k elements first before this guy. So we will add vi times k to my result. Or this guy could be either 0 or negative, in which case it's better to pick this guy first so that this negative value doesn't reduce your final result. So you would pick this guy first and then k later, and the contribution to this interval will be 0. Alright? Okay, so this solves the problem if there are no restrictions of which guy can take at any time, right? But that's actually easy to take care of because at any moment when I'm looking at an interval, either this guy here is the last element of the array, which is I minus 1, or or this guy here was already taken, right? Because that's how I calculate my, should I pick an element here and how recursive for each part. So this invariant holds. When I call recursively by function to the interval, either the guy to the right comes before a guy that I just chose, or it's the rightmost element of the array. In both cases, we know that we don't have to worry about any restriction that starts here and ends here, right? Because the condition for a restriction, I think they call it, what they call something. Doesn't matter. The problem imposed the restrictions, which was a pair of x, y, and this means that either x or y could not be taken if all elements between x and y were still present. But in this case, if we have a restriction of this type, then I wouldn't need to be worried about it because I know that this element is taken, which means that this restriction is not active anymore. Right? So I don't have to worry about restrictions that lies entirely inside the interval that I'm currently looking at. Right? Some restriction like here, I don't know. And this guy has come before this one, for instance. Right? Suppose we have such restriction here, and you cannot take x before taking any element in this interval. So in order to check whether there is a restriction that prevents you from taking this element or not, you can just, for each element, find what is the, among the guys that restrict this element, which one is most strict. Right? So there can be many restrictions preventing this guy from being taken. The only one that matters is the one that is closest to him, right? If this is active, then this is active and this is active. So for each guy, you just find what is the strictest restriction you have for both directions. And if this guy lies inside the interval you're looking at, then you cannot take this element. Right? So that is one less possibility for this. This is actually a maximum of all eyes. If this happens, you cannot take this either, so you have to consider other eyes. And that was pretty much it.
Isn't this n to the fourth?
Yeah, it's n fourth. And plus. Sorry. Yeah, n was 150, so you might be worried. So n fourth is close to 5, 10 to the 8th power, or 9th power. Is it 9? I think it's 10. I didn't. It wasn't that. Yeah, it's the 8th power. So this is scary, but it's
divided by 6, yeah.
Yeah, divided by 6. This should be good, right?
And it should do with interaction because of the memory.
No, that's true. Okay, they're recursive.
No, the memory is
Yeah, memory is absolute.
okay.
Yeah, you might be worried about the time that you could try something that this DP recursively, but that's not necessary. I thought I did recursively and see if I understand it. So yeah, that was the solution to this problem. Any comments, questions? Yes.
The restriction part, did you understand?
So let me explain that. So the restrictions for the form x, y which means that x cannot be taken before. This means that if every element between x and y you're not taking yet, then you cannot take x. Right? This was a restriction. So, but y could be either less or greater than x. Right? Suppose that y is greater than x, the other case is similar. 2, 7. So the second element, so if at some point you haven't chosen any element between 2 and 7 yet, you cannot take the second element. Right? Okay. So suppose that I'm currently calculating the optimal answers for some interval from L to R. Okay. So I'm going to have two possibilities. Either R equals n minus 1, which is the last element of my interval, or this guy here was already taken. Because this is an invariant that my dynamic programmer maintains. Suppose that this is true. This is true for the initial array. For the initial array, R is n minus 1. Okay. Now what I'm going to do is pick one element here in the middle and recursively calculate the b for these two parts. Right. Now the first path satisfies this inequality, this invariant, because the next element would be this one, we should have just picked. And for this guy, this is the right closed element of the array. So this also respects the invariant. So whenever I'm calculating the optimal answer for an interval, I can safely assume that I don't have to worry about restrictions of this kind, such that the y value is to the right of this extreme of this point of the interval. Okay. So, and also for each x, you can calculate what is the minimum y that restricts x. So the only thing you needed to know in order to check whether one element was restricted or not was to check whether this minimum y lies in this interval. This is less than r. If it is, then this whole restriction here lies inside the interval. You haven't picked anyone from here yet, so this guy cannot be taken. Otherwise, if this minimum y lies here, then this restriction is not active anymore because this guy was already taken. Okay? Cool. Any other questions? Comments? Rants? So, I don't have anything else to talk about, so I guess we can't go too much earlier today, unless you guys want to talk about anything.
I think there is one problem.
Is there?
No. Oh no.
This is still true. Today's conference will start at 13:45.
Mas espera que eu não sei o que falar.